what the compound interest formula did. And basically it takes all those little calculations we were doing in like those two problems we just went over in the homework with simple interest, but it does them all combined inside the formula somehow through the magic of mathematics. And this is the formula. This is your principal. Okay, and this is a single deposit. So this is, again, like the simple interest formula, this formula is limited to I deposit this money in the account one time, and I just let it sit there for however long. Okay. R is your rate, again, as a decimal. N is the number of times we compound per year. T is the number of years, or time in years. If it's less than a year, you've converted it with, fraction or decimals, which we will go over. And then B is our balance at the end. Not just the interest, but the actual amount of money that will be in the account, the total. All right, so Maria deposits $16.50 for 3 years at 3% compounded daily. All right, so first we have that's our formula. All right, so our balance is going to be our principal. Our rate is 3%, so it's 0.3. N is 365. And we have 365 times 3 years, so times 3. Okay, so for that next step, I'm going to divide 0.03 by 365, and I'm going to get 0.00008219 some other stuff. And then 365 times 3 is 1095. And then I'm going to add 1 plus all that, and I'm going to get 1.00008219 to the 1095. Then I'm going to raise this to the power of 1095. And I'm going to get 1.094 and some other stuff. And then I'm going to multiply those two. And I'm going to round to the nearest penny because we're talking about money and we don't have parts of pennies. Okay, so without writing it all down, what I'm going to do is I'm going to write down this part, still the same. The very next thing I'm going to do is I'm going to do my exponent, 365 times 3. And I'm going to cross this out and I'm going to write that down so that I don't lose it. Okay. I won't have to write down anything else now until I get to my answer. I take 0.03, I divide it by 365. So I do this part first, plus, whoa, that's not right, 0.03 divided by 365. Oh, to e to the negative fifth. Yeah, it is correct. Sorry, I missed that bit. Plus 1. So now I've done what's inside the parentheses. To the power of 1095 times 1650. Okay, so to label this, I guess this was technically first, just finding it. So I do this, then I add, then I raise to the power of, then I multiply. So I'm working inside out. And then you don't have to write down all of this stuff. And I didn't do any rounding at all in the whole process, so my answer is the most accurate. Because I was not going to write down all those digits. That's why I put those dots there. And I certainly wasn't going to type back in all of those digits. So this way, if you hold them in the calculator, if you go in that order, everything will just be held in the calculator. Just do the next part to it, and then you've got your answer. And as far as for your grading for full credit, if you have this equation set up and I can see that you did the exponent and then you put down the answer, that's all the work I need to see. Will either be this little thing right here, button with that little caret, it's called a caret, or x to the y, or y to the x. I believe Casios have the y to the x. TIs, depending on which version, have one of these two. And then as you can see here, this has the x to the y. The Apple calculator, when you turn your phone sideways, has the x to the y. So remember we talked about the percentage yield is a little different than the percentage rate. The yield is the percent of money you actually earned. Okay, so first we have to figure out the interest. Actually, first we have to find the balance. I'm lying to you. First we find the balance. Second, we find the interest. And then third, we find the yield. Okay. All right, so for the first part. Okay, I have $8,000 in a 1-year CD at 0.032, that's 3.2% interest compounded daily. So 1 year, T is 1 year, but I have 365 times 1. And just to get myself into the habit, I always go ahead and do that. Then I'm going to take that 0.032 divided by 365. See here, that E is negative, so that's the scientific notation. Plus 1 to the power of 365 times 8,000. So 8260.13. Okay, so that's the balance at the end of the year. Now to find the interest, I take the balance and I subtract the principal. Okay, so that's the interest. Okay, and then to find the yield, I take the interest and I divide it by the principal. So I take that 260.13 and I divide it by the 8,000 that she initially deposited. I'm going to turn that back into a percentage. So I've got 1, 2, and it said to the nearest 100th of a percent. Okay, So her yield is 0.25. The pay was 0.2. So it's slightly higher. Okay, get the notes and the assignment off the Sky. Not a lot higher, but it is a little, the yield is a little higher. So when the banks advertise, they'll advertise this because it looks better than that. In calculus, there's this concept called a limit. And we have functions in math that never reach a number, either because they go off into infinity. For example, if you look at a parabola, and these keep going up and up and up and up forever and ever and ever, and so they have no end. Or we have functions, the decay function that goes like this, and this line here will get infinitely close to the axis. So I mean, where you're talking about fractions that are like 1 over 500 billion. And I mean, just tiny little, tiny numbers, tiny numbers. It gets so close to the axis, but it never actually touches the axis, ever. The fractions just, the denominators of the fractions just keep getting bigger and bigger and bigger and bigger, but you never end up with 0. Well, what the limit does is it takes these unreachable things and it assigns a number to them. So what happens, okay, so what the limit does is it'll take these values that you can't reach. And in math and in calculus, the limit says, okay, it's really close to 0. Like this one where I said the fractions get tinier and tinier and tinier, but never actually touches 0. But it gets so close to 0 that it might as well be 0. And that's what the limit does, is it says, well, it's close enough, we'll call it 0. Okay? And you can have, every function will either have like an actual value or a limit or no limit. If it has no limit, it's infinity, like this one. This one has no limit, it just keeps going forever. It doesn't ever get close to anything. It just keeps going. Whereas this one gets close and close and close to this 0 axis, so the limit is 0. And then if it actually touches a number and that's the end of it, that's just the value it is. It doesn't have a limit, it's just, it is 5 or something. Okay, and limits deal with the concepts of finite and infinite. Anybody ever hear somebody say that infinity is their favorite number? No? If you ever hear somebody say infinity is their favorite number, now you can laugh at them. Infinity is not a number. Infinity is what? If they said infinity was their favorite number? Yeah, it's not a number, it's a concept. So finite can be represented by a real number, it's measurable, and it has an end. This room is finite. Our lives are finite. The length of our arm is finite. Infinite is not ending, it's not measurable, and it is not a number. There is no such number as infinity because, okay, let's say infinity was a number. Then you could add 1 to it, and then what would it be? Infinity plus 1? No, that's just still infinity. It just keeps going and going and going. So this is what limits do, is they assign a finite number to an infinite concept. And infinite numbers can give you a finite sum. And this is one of those things that where your brain just goes, nah. But let's say the room is 64 feet. It's not, but let's just say it is. Halfway across would be 32 feet. Halfway across that would be 16 feet. And I could cut that 16 feet in half and I'd get 8 feet. And I could cut that in half and I'd have 4, and then 2, and then 1, then half a foot, a quarter of a foot, an 1/8 of a foot, a 1/16 of a foot. And I could keep cutting it in half forever. And I could end up with these fractions that are ridiculously small. Hold on, let me come up with a number real quick. Let's do 2 to the 20th. Okay, I could end up with, I've cut this in half 20 times now. After my fraction, my half, I've cut it in half 20 more times. So I end up with a fraction that's 1 over 1,048,576. And then I can cut it in half again. And each of these can get cut in half until all of the pieces are that small. Right? This 32 could get cut in half and then cut in half, and these can all be cut in half. And I could cut them all in half until I have these fractions that are tiny, and I could keep cutting it in half. But when I stick it all together, it's still 64 feet. Right? The room didn't get bigger just because I was cutting it into littler and littler pieces. So I can have an infinite number of tiny itty-bitty, can't measure them pieces. But when I stick them all together, it's still going to be 64 feet. And this is something known as Zeno's paradox. Is that you can have infinite number inside of a finite space. And that's another thing that leads all to the way we're able to do what's called continuous compounding. Continuous compounding is compounding infinitely many times. So we do infinitely many calculations, but we get a finite number. We get a finite interest. So if I make a t-table and this is the value I plug in for x, and then this is the value that this gives me back out. So if I plug in 100, I get 600 minus 1 divided by 302. So 599 divided by 302. And that gives me 1.983443709. And if I plug in 1,000, I get 1.998334444. And if I plug in 90,000, yeah. So this would be like 6 times 100 minus 1 divided by 3 times 100 plus 2. So you get 599 divided by 302. And then you divide that, and that gives you this. And so if I plug in these numbers and do this math, I just want to show you what happens. And then I plug in 8 million. 1, 2, 3, 4. Okay, I have now plugged in 2 billion, and I'm at 1.9, and then there's a whole bunch of nines repeating. And I could plug in 20 billion, or a trillion, and I'm still going to get 1 point and then a bunch of nines. No matter what I plug into this, I'm going to get 1.9 something. I won't get anything that goes above 1.99999 with all these nines. I'll continue to keep getting nines. So what happens is this one has a limit. And so what we say is as x approaches infinity, that's the symbol for infinity, the function f of x gets closer to 2. But we never quite meet 2. And the way we write that mathematically is is like that. The limit of f of x, that's the function, as x approaches infinity is 2. Talk about it here. All right, we can't actually calculate this with our regular calculator. What happens when you have this right here and you do the calculus, you get a number called e. Okay, e is the base of the natural logarithms, and I shouldn't put equal because it doesn't equal. It's about 2.718, and then it has more digits, but it's like pi in that we just round it and use 2.718. And e is the base of the natural logarithms. It's a mathematical concept, mathematical constant. Okay. And what we get at this point is we get 1,000 times e, which is 1,000 times 2.718. So we would get $2,718. So if you put $1,000 in the bank for 1 year at 100% interest for continuous compounding, you would more than double your money. Now, continuous compounding is happening an infinite number of times per year. So it's like every nanosecond is calculations are occurring. Except that would take up a lot of computer power, right? So the formula uses limits, or limits were used to derive the formula to figure out what the result of all of those infinite number of compoundings would be. And we get the balance is equal to P-E-R-T, where B is the balance, P is the principal, E is 2.718, R is your rate as a decimal, and T is time in years. So that's the continuous compounding formula, PERT. So we put in $1,000 to the 0.043 times 5 years. So first I'm going to do this 0.043 times 5. Of course, I closed my thing. Okay. Then I have, Okay, this calculator doesn't have an E button, but my actual calculator has an E button. I don't know if the phone calculator does or not. Hold on one second. You can, if you want to. I was going to say there's usually a button. If you want to just push the button, you can just push the button. Because when you do, hold on a second. Let me pause this for 1 second. You would think that continuous compounding would give you like so much more money, right? Because it's infinite compounding. But if we do the normal, and we'll do every day. This is regular compounding, not continuous. So I'm doing daily compounding, just so you can see the difference. like just for comparison. So infinite numbers of compoundings in 5 years, or 1 time a day for 5 years, gives you a whopping 2 more cents. So like you would think that that continuous compounding would make a huge difference because it's infinite, right? It's infinite compounding, but each calculation on those is microscopically small. So they don't add up to that much more.